SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 4, that is Hydro and Renewable Energy Power Generation System. So, in our previous lecture, we are focusing on energy storage part 1. Now, in this lecture, we will be focusing this energy storage part 2, where we will be discussing about two important energy storage systems, that thermal sensible and latent heat energy storage. And in particular, we will be discussing about the pressurized water based sensible storage systems, which is a very common type of applications, and we call this as a steam storage. So, first thing that I need to emphasize that we need energy storage because it is the only options that can cater the peak demands for any kind of power plants. We know that for renewable energies are always intermittent in nature. They vary hourly, daily, monthly. So, in order to run this plant continuously with steady energy, we require the main plant to operate at a base load, and during the off peak hours energy can be stored, and this stored energy is utilized further to cater the peak demands by the users. So, for that energy storage is the only options, but however, this energy storage is possible in mainly in two methods. One is electrical part, other is the thermal storage. In our previous lecture, we talked about this electrical storage, or we call this as electromechanical systems. So, in which the storing is mainly based on potential energy. So, for that we discussed about pumped hydro storage and compressed air storage systems. Now, in this lecture our focus will be thermal energy part, and in this thermal energy part we will be talking about one is sensible heat based thermal energy storage, other is the latent heat based energy storage systems. And in any case we say that primary plant operates at base load, and whether it is electrical mode or thermal mode, but the peak load plant has to be catering the need of the user at the time of demand. So, the advantage of this thermal energy storage system is that we can have a wide choice of system materials, and they can operate in the range of refrigerating temperature to 1250 degrees centigrade, which means refrigerating temperature, I mean it is not exactly 0 degree, which is for water, but there are some materials which has capability to store the energy maybe below sub-zero. So, for that things the possible methods we can have is that we can talk about pressurized water storage. So, this is nothing but we call this as a steam storage, and which is very common in large scale power plants. Other methods involved like organic liquid, packed bed, solid bed storage, and fluidized bed storage. And these pressurized water based systems we call this as a steam storage. This is something similar to case where we store air to run an air turbine. Here we store steams with certain techniques which can run the peaking turbine at the time of need. Another advantage of this system is that it can be integrated with any kind of power plants or base plants which can be operated through nuclear reactor or any fossil fuel furnace. Here entire idea is that base load plant supplies steam during low demand, so that excess steams can be bled at high pressure turbine extraction. This is something we call this as a feed water heating systems or regenerative mode of operating in a steam turbine for a conventional power plant. So, whatever you tap the steam at low pressure, that can be stored. So, this is how the system operates, and we see this thermal circuit diagrams. So, what we see is that we have two turbines, one is for main turbine, other is the peaking turbine. Main turbine runs at base load. Now, from this main turbine we tap some heat at certain locations, and this is something called as regenerator mode of operations, and that steam we are storing in an accumulator or in a large structure. We call this as the steam accumulation systems, and in fact these two units are called as steam storage unit. So, this is stored at certain pressure and temperatures, and when the steam is stored it is packed with water. So, that steam is mixed in water medium, and we call this as a saturated water saturated conditions, either it can be saturated liquid or vapor. So, this steam accumulator operates at saturated conditions, and this is other options are similar to this, same as that. So, you have steam generator that is run from the primary heat sources, and rest of the things are same except the fact that we have one unit which is called a peaking turbine. So, these two turbines are to be operated separately, because this peaking turbine work on saturated vapor, because that expands in the turbine, whereas the main turbine we can have superheated steam. So, during the demand hours, steam whatever stored in that manner, it gets pumped back to the peaking turbine to generate power, or that is for peak demand, peak load operation. Now, here some of the silent features are that peaking turbine operates when there is a peak demand, and which means that accumulators are discharged in these small peaking turbines. The operating limits typically fall in the range of 20 bar, for which the saturation temperature is of water is 212 degrees centigrades. Lower limit is 2 bar, for which saturation temperature of water is 120 degrees centigrades. So, range of temperature is 120 to 212. So, that any point of time we will find only steam, not maybe dryness fraction should not come below 1. The main important parameters to quantify this peaking turbine steam generator assembly is that one is thermal turnaround efficiency, other is peaking turbine generator efficiency. So, typically this peaking turbine generator efficiency are kept at low, because we are operating the steam at only saturated region. So, it is in the range of 20 to 25%, and also the base load plant operation falls in the range of 30 to 40%. So, this is what the conditions, and this is mainly because of variable inlet conditions, low temperature of saturated system, small size, and there are so many other factors. But however, our main part of our analysis, this because it is charging and discharging steam. So, for that we call this as a thermal turnaround efficiency, and this thermal turnaround efficiency is a complex functions associated with the sensible transfer of heat to and from the steel wall, which means steam is stored in a container which is made out of steel, and idea is that the steam the rate of heat loss should be minimized. So, steam contains energy, and also the wall material is also made out of steel. So, the conditions are such that heat losses are minimized, and also other losses are structural members, interconnecting pipe, but main losses that comes out for, that is a main parameter for thermal turnaround efficiency, is the time dependent convective heat loss, which we are going to analyze. So, to quantify this pressurized water sensible stereo systems, we have some parameters. First parameter, it is called as storage density. So, storage density is a pressurized water storage medium, and which can be expressed as a function of product of temperature difference, specific heat and thermal density of the materials. So, what we see is that the steam accumulator is made out of steel, and whatever heat that gets stored in the steam is supposed to get conducted out of this accumulator through this wall, and that wall and the capacity of heat capacity of the wall is nothing but this temperature difference, specific heat and density of the material. Other parameter is that the storage density of is also utilized, and one more other thing is that other way of quantifying this is for storage thermal density, that is utilized in the peaking turbine per unit volume of high pressure saturated water, which means if you look at this expression, we are trying to express the storage density as a function of power generating factor. So, for example, in this case if your system operates between 20 bar and 2 bar, so we can correspondingly find out what is the enthalpy at 20 bar, saturated value of enthalpy at 20 bar, and saturated value of enthalpy HF value, the liquid enthalpy, that is 504.8 kilojoule per kg at 2 bar. So, correspondingly at storage pressure, specific volume of water would be around 0.001176 meter cube per kg. Now, from this we can define a storage density as a function of how much stored capacity of volume of water you require per kilowatt hour. So, in this case we can say for this enthalpy difference, and or we can say for this pressure difference between 2 bar and 20 bar, the storage capacity could be as high as 95.3 kilowatt hour per meter cube. So, that means if your storing limit is 20 bar to 2 bar, then the steam has a capacity to store about 95.3 kilowatt hour of energy per meter cube per meter cube. So, larger the meter cube, higher will be the capacity, which is means it means. Other part is the steam which is gets accumulated. If I say this is an accumulator, and this accumulator has wall which has certain thickness, and this thickness is defined as T, and also this diameter and length as defined as D and L. So, the heat as to gets as to the whatever steam which is stored here, it has energy which is available from the steam, and it will try to get convected out of this wall. So, there are two parameters here, one is wall material in which it is stored, and typically it is steel. Other is which is steam which is stored closely at about 20 bar pressure. So, what the idea is that there are two factors, one is energy dissipated at the solid wall which is this, and energy stored in the accumulator in the steam. So, it is a cylindrical steel container with dimensions D, L and T. So, two things can be quantified here, one is stored capacity for material, solid material rho s and Cs, and store capacity of the steam. So, rho f and Cf, that is density and specific heat of fluid and density and specific heat of solid, and this is of order of same order, that means they should have same capacity. Other thing is that if you talk about storage pressure, and this storage pressure has to be withstand by this wall. So, for that we call this as a wall stress which is sigma, and this ratio that is P by sigma is of the order of 0.03, which means that kind of material we should choose. So, steel is the best choice, and considering these two energy ratios E d by E s, it can be turned out that this numbers is so less that energy dissipation is conventionally ensured, that there is a minimal dissipation of energy which is from the stored steam. So, only possibility that energy can come out from the system is through convection. So, for that things we say that convective heat loss from the water to the environment is a major contributor for the thermal turnaround efficiency. So, we will try to find out thermal turnaround efficiency for this kind of pressurized sensible heat storage systems, and for which what we can try to understand. So, this particular model can be analyzed as a lumped heat capacity model, which says that if you have some lumped capacity model theory is that if you have some in this case it is density of the fluid, temperature and volume, and this is your surface, and this surface has area A and outside temperature is T infinity and heat tries to comes out, which is Q by convection. So, there are two parameters are involved. One is the thermal resistance and that is for fluid and for solid, and this is justified by considering the fact we introduce a parameter which is called as Biot number, and this Biot number is much less than 1 and it is defined at HL by K. H stands for fluid property, which are fluid convective heat transfer coefficient for fluid. K stands as the thermal conductivity of the solid. So, what it says is that at when you say lumped capacity model, we imagine such a systems that initially we have a stored temperature T1 and suddenly when it sees this ambient temperature it tries to comes down. So, through this process, assuming that if the system is completely insulated, we say there is no heat loss, but if there is a heat loss through convection, so system can start from initial temperature to final temperatures. So, final temperature becomes T2, but what we require is that the steam accumulator should have some capacity, it should store the steam for certain time. So, we call this as a we call one more parameter what is called as storage time theta s, and correspondingly the temperature we call this as a Ts. So, the relation between T, Ts, T2 and theta s can be formulated based on this lumped capacitance model, and we can assume this Biot number to be much lesser than 1, and that is possible and the theory for this is shown here. So, for any heat transfer book we will talk about the expressions of temperature distribution at any time instant t, and where t at any time theta minus initial temperature is t minus T infinity minus T1, T infinity minus T1 means it is the outside temperatures. So, it starts with initial temperature T1, final temperature T2 and Ts is the temperature if you talk about for which theta s is your storage time. So, considering this one can have these equations. So, here this is an exponential decay from initial temperature T1 to final temperature T2 and this is theta 2. So, this exponential decay contains a term called as tau, and this tau we call as a time constant, which is defined as the ratio of heat capacity to heat flow resistance. So, for this we can have this heat capacity in terms of fluid, that is pi by 4 d square L into rho f into Cf. This is your volume of the tank, cylindrical tank, and also heat flow resistance is can be defined as a function of overall heat transfer coefficient U. So, pi dl into U. So, putting this we can define this time constant T this, and so that at if you say you have a storage time theta s, corresponding temperature is Ts. So, this equation gets reduced to Ts minus T1 divided by T infinity minus T1 is equal to 1 minus T to the power minus theta s by tau. Now, we are going to talk about thermal turnaround efficiency. So, basically we have some storage initial time T1 and T2. During these things this enthalpy difference would be H1 minus H2, but we are actually looking at the storage time theta s for which enthalpy can drops from Hs to H2. So, from this we can enthalpy can be expressed in terms of temperature, and this temperature finally, I mean Ts we can find out from the above equations. Putting this, we find out a thermal turnaround efficiency term as a function of initial temperature, final temperature and free stream temperature. And here this is actually our expressions for which we define this thermal turnaround efficiency for a pressurized water sensible storage systems, and this will help us that how long we can store this pressurized steam in this accumulator. Now, from this we can get some inferences that thermal turnaround efficiency is a strong function of ratio of storage period and time constant. So, higher value of time constant will result higher thermal turnaround efficiency. So, main intention of design of steam accumulator will have that we should choose higher value of time constant. But then to choose this higher value of time constant, we can say that the overall heat transfer coefficient should be minimum. So, that overall heat transfer coefficient is a complete function of the thermal resistance that occurs for variety of mode of heat transfer like conduction as well as convection, and also depends on the volumetric heat capacity. So, this is the reason that we need to have overall heat transfer coefficient as low as possible. Now, to since we cannot have any control of time constant because it is a complete function of so many parameters, but what we can have control is that choice of fluid and choice of overall heat transfer coefficient. For that reasons, one can think of this accumulator can be kept above ground or underground. So, this is what the idea that can be explored for choice of accumulators. Now, next thing we are going to move is that latent heat based energy storage systems. So, when you say sensible heat storage, it is basically the temperature difference that plays a role. But when you talk about latent heat, where we say that there is no change in the temperatures, we can think of some phase change materials that continuously vaporized and continuously also condensed. So, through this process we can store quite substantial amount of energy, and it in fact here also we talk about storage density, which is equal to product of latent heat times vaporization to the density of the storage materials. Moreover, these latent heat based storage systems are more efficient than that of a conventional sensible heat type of storage systems, which involve single phase materials, because the heat storage occurs at single phase only. And we have a choice of wide choice of materials which with different fusion and evaporation temperatures. So, this will allow that we can have wide range of operating temperature and pressure range, and it also this have ability to generate high temperature of steam at the peaking turbine. But only drawback is that this choice of materials with their fusion and evaporation temperature, that has to be judiciously chosen for a reliable operations. And of course, it is not considered for large scale power plants is not considered as a viable options, but it can do some kind of justice if considered, if the cost factor is taken care. So, why it is so? Let us try to understand here. So, typically this is a flow diagram for a latent heat storage, in which we have a high temperature gas cooled reactor, and this reactor supplies necessary steam for running this base turbine. So, that is what we call as base load. For base load operation, this is a conventionally Rankine cycle based operations, the turbine operates and for base loads. But what extra feature which is added here, a fused salt reservoir, which is nothing but your latent heat based storage unit, and this salt absorbs necessary working fluid, that necessary working fluid which is called as a secondary fluid, and here the secondary fluid is your PB that runs in the circuit of this fused salt reservoir and this main plant unit. So, what it does is that during we take out some steam to this circuit, and maybe we take out some heat to add energy to this fuse slot, and also side by side the energy from the this helium circuit also can be added here. So, thereby the salt fuse salt gets necessary heat, so that it get energy stored here. Now, during the discharge period, this energy can be released to cater the need for the peak heating hours. So, here the main plant although operates in mode of water as a primary working fluid, but other circuits involved the materials like helium coolant. Here we require lead for this fuse slot operations, and this what is this fuse slot, I will come back later. So, this fuse slot requirement or choice of this fuse slot and with their combinations is a very vital for efficiency of this plant. So, that is the reason although this plant is not typically considered as a better options, but at the time of requirement this can be considered as a possible solutions. So, the efficiency of these latent storage systems mainly depends on the what type of fusion salt requirement we have. So, for that reason here we have mentioned some of these requirement of the storage materials. For the storage materials for latent heat storage must possess proper transition temperatures, high latent heat, good thermal conductivity, stability for cyclic phase change operation, that the working fluid should be also non-toxic and low cost. But however, all these things cannot be achieved by any particular materials. So, no material meets these requirements, especially we need to explore some fluoride salt which has to be designed. So, one such possible choice is what is called as eutectic salt. It consists of sodium fluoride and iron fluoride with a combination of 70% sodium fluoride and 30% iron fluoride. It has a fusion temperature of 680 degree centigrades. So, that means they can be stored at till that temperature. Now, when stored at this temperature, they have a possibility of storage density to provide that 1500 megajoule per meter cube. And of course, other materials like zinc chloride will have storage fusion temperature of 370 degree centigrades. They can give a storage density of 400 megajoule per meter cube, and the for a typical unit which is sold in that circuit, which is called as eutectic salt, which is operating with helium coolant of 48 bar, one can explore that storage capacity can be of 70 to 100 megawatt hour, and charge discharge rate can be 600 megawatt. So, it means that you store this energy, but this energy you store, but when during charging and discharging rate it can operate at 600 megawatt power. And through this process one can think of getting 200 megawatt power for about 12 hours. And if you want to achieve this with that thermal conceptual circuit, we require a eutectic salt of 42,000 tons. Storage vessels will have diameter 36 meter and height 30 meter. So, it has to be contained in a high wall stressed type of storage materials, typically steel, and if want this cyclic efficiency or thermal turnaround efficiency would be close to 90%. So, this is just a kind of a conceptual design or idea for a latent heat based storage systems, which is anyway it is a conceptual designs, but it can be considered as one kind of storage unit. Even not today, maybe in future this choice of this particular storage unit can also be explored for a large scale power plant systems. So, with our discussion today, we will try to solve a numerical problems in which we talk about a pressurized water based sensible storage systems in which heat losses are quantified mainly by convection, and the entire idea of this heat loss is modeled through a lumped heat capacity model. The necessary theory for this lumped heat capacity model I have mentioned in this lecture. So, I will be using only those end results to give the glimpses or the idea that how this pressurized water based storage system works. So, essentially it is a nothing but a steam storage, and operation is quite similar because it works on the simple principle of Rankine cycle. So, the solution of this problem starts with the fact that we have the steam accumulator unit. This steam accumulator unit has certain parameter, and the steam has to be stored at 20 bar and 2 bar. So, upper limit of 20 bar and 2 bar pressures, and for this we can using steam table we can find out saturated values. So, this we call this as a saturated condition. So, for this we can have higher temperature, upper temperature T1 as 212.37 degree centigrade. It has enthalpy values 908.5 kilojoule per kg, and corresponding specific volume at this stage is 0.0011766 meter cube per kg. Similarly, at 2 bar we can note down the saturated temperature is 120.23 degree centigrade. HF2 becomes 504.8 kilojoule per kg, and VF2 is equal to 0.0010605 meter cube per kg. Now, since we know this volume, so we can find out as average density, because we require to find out the time constant, for which we require average density of steam which is stored, that is rho is equal to rho 1 plus rho 2 by 2, which is at these two conditions. So, this can be written as 1 by 2 1 by Bf1 plus 1 by Bf2. So, it is 896.43 kg per meter cube. So, we get this average density. Now, then we can find out time constant. We recall this time constant expression tau as d times rho f Cf divided by 4u. So, rho f we got it, Cf like for water this C specific heat is 4.35 kilojoule per kg Kelvin. Overall heat transfer coefficient U has been 5 kilojoule per hour meter square Kelvin. Diameter is given as 4 meter. So, time constant turns out to be 781 hour. So, the first expression that we need to find out what is the thermal turnaround efficiency. Tau efficiency turnaround, that is we can recall this expression as 1 minus 1 T1 minus T infinity divided by T1 minus T2 entire bracket 1 minus e to the power minus theta s by tau. So, the value we have T1 is given, T2 is given, and T infinity we can say ambient condition as 20 degree centigrade. So, storage time theta s is equal to 15 hour, storage time is 15 hour. So, putting these expressions we come back this turnaround efficiency is equal to 0.96 or approximately 96%. Next question that is asked, what is the total volume? So, to find this total volume, we require the information from the peaking turbine. So, we have this peaking efficiency as 25% and we have storage capacity of 4000 megawatt hour, which is the power. If this power has to be operated with 25% peaking efficiency, so we require the storage energy, stored energy PS would be 4000 into, because it is hour, so it is 3600 second into 1000 divided by 0.25 is your peaking efficiency, and we also have the turnaround efficiency of 96%, 0.96. So, putting this number, we get the stored energy will be 6 into 10 to the power 10 kilojoule. Now, for the stored energy, we say mass of water, because it has to be sensible storage, that is M would be PS divided by HF1 minus HF2. So, 6 into 10 to the power 10 divided by 908.5 minus 504.8. So, this number is 1.5 into 10 to the power 8 kg. Then once you know this mass, then volume can be found out. Volume is equal to mass into specific volume. Total volume will be mass times its specific volume. That specific volume we talk about 20 bar pressure. So, this we can say 1.5 into 10 to the power 8 into 0.0011766. So, total volume would be 174,840 meter cube. So, this is the volume of steam. So, accumulator volume should have, which is minimum size should be of this range. Then next part is minimum energy release. So, minimum energy release E minimum would be E stored minus E ambient. So, E stored is M into HF at 20 bar, it is minus M into H infinity ambient. So, this becomes minimum energy release would be 1.5 into 10 to the power 8, that is mass, enthalpy at 20 bar, that is 908.5 minus at 20 degree centigrades. Your free stream enthalpy we can note down as 293 Kelvin. So, this will give you minus 293. So, E minimum becomes 9.2 into 10 to the power 10 kilojoule. That means, the steam can give a minimum energy which is can be released from this is this. And last part is cost, the cost of the accumulator. So, it is given that unit volume cost is rupees 25,000, total volume is this. So, cost of accumulator we can say minimum cost for the accumulator would be rupees 25,000 into that is per meter cube, and total volume is 174840. So, this is rupees per meter cube. So, meter gets cancelled. So, minimum cost would be rupees 4371 lakhs. So, approximately it is 4.371 crore. So, you can say that it is a huge cost of investment, initial cost of investment. So, but however, you can see that how much energy that can be released from this, and we can talk about power requirement of 4000 megawatt hour. So, why these numbers are important? Because energy storage is justified only when we are storing it at very high conditions, because the infrastructure requirement is huge and involvement cost is also high. So, then only the choice of a power plant with an energy storage integration with energy storage systems will be justified. So, this is all about today's lecture. Thank you for your attention.